Jan Solihin. So today we are going to cover Introduction to Memory Hierarchy Organization. So we're going to look at the basic of cache architecture. So first of all, what is cache? Cache is essentially a temporary memory, temporary storage that is close to the processor. So if you look at an example here, this is some system similar to IBM Power in about 4 years ago. So you have processors P right here, processors, and then you have a hierarchy of memories spanning from level 1 cache. So D and I are essentially level 1 cache. D is data cache, I instruction cache, and then level 2 cache, and level 3 cache, and level 4 cache, and then the main memory. So the key thing to know is that as you go down further away from the processor, the size of the cache increases. At the same time, it's also slower. Okay, so this makes sense because larger structure will be slower. So in the following example, you can see that L1 cache 32 to 64 kilobytes in size. L2 cache is 256 kilobytes to 1 megabytes. And note that both the L1 caches and L2 caches are private per core. But as you go down, then they start to become shared. Okay, also the reason for this also makes sense because as you go further away from the processor, you want the resources to be shared so that there is no resource fragmentation. Right, and then outside the processor chip, you see a level 4 cache in this system. Now, not all systems will have an L4 cache. Finally, you have the main memory. Now you can see the progression in terms of access latencies, starting from only a few clock cycles for L1 cache, all the way to tens of clock cycles for level 4 cache, level 3 and level 4 caches. Okay, so why is main memory organized this way? So the reason for this is that the time to access the main memory. Okay, so anytime the processor needs some data, if it misses, if it needs to read it from the main memory, it takes a few hundred clock cycles. Okay, so obviously that's too long. So the way to mitigate that is to provide a temporary memory called cache, such that the data that you want can be found in the cache in just a few clock cycles. Now, obviously, if you can't find it in your cache, you have to go to the memory again. Now, because the gap is so big in access time, then you provide multiple levels of caches. All right. So now let's think about a single cache. Okay, so you can think of a single cache as a table. Okay? It essentially stores cells of data. So in cache terminology, it will be called cache lines or cache blocks. Okay? So if you have a table, you will have a number of rows and a number of columns, and that will be the size of the cell. In cache, we will have a number of sets. Number of sets essentially are number of rows, and the number of columns is called the number of ways or associativity. Okay? So we have number of sets, associativity, and then each of the cell is essentially a cache block size. Okay? So it's quite similar to a table. However, there are some differences. Okay? So the first is that a table doesn't specify where you want to put data, right? But in a cache, you have to have a placement policy and replacement policy. So when you bring in data from memory, you have to decide where can I put the block in the cache. Second is that if you run out of space, you have to also define which one you should evict from the cache. Alright, so one constraint that cache designer come up with early on is the following. Okay, so if you so this is related to the placement policy. When you bring a block from memory, the constraint is that you can only place that block in one set of the cache, essentially one row, okay, one set. Because of that, then the cache can be organized in different ways. Okay, so for example, in a direct map cache, it will be like one single column, many rows, okay, or many sets. Now, if you have a block, let's say block X, from memory, it will be placed in one particular set. And because each set has only one way, then there is only one place for it to go. And because of that, then this is called direct map cache. You could also have the other extreme, meaning that you have a fully associative cache. So you have one set and you have a lot of columns or a lot of ways. In this case, if a block is brought from memory, it can be placed anywhere in the ways. Okay, so that's the opposite of direct map cache. But in most cases, a cache will be organized as an associative cache, meaning that it's not a single column, it's not a single row, but you have a certain associativity, right? So let's say in this case, four-way associative, okay? And in this example, this is two-way associative. Alright, so what are the trade-offs of the associativity of a cache? Okay, first is that fully associative cache allows very flexible placement of block in a cache. Typically, this means that you're going to have a low miss rate. So you don't end up in a situation where some of the sets are utilized, some of the sets are not utilized, something like that. So in this case, because every block will map to the same set, then the set will always be well utilized. The problem is that it's power hungry, okay? Because there is so much flexibility. When you want to locate a block, you essentially have to check all the existing ways, okay, all the ways in a cache to figure out whether the block is in a cache or not. So it's power hungry. Have to do a lot of type comparison. So the opposite of that is direct map. As I mentioned, it has a very rigid placement of a block in a cache. So a block can only go to one specific cache line. So typically this will result in a higher cache miss rate. In fact, the difference between this, the direct map cache and fully associative cache is oftentimes called as conflict misses. Okay? So it has a higher miss rate, but very power efficient. You actually, you will not be accessing all the ways in order to compare the addresses. All right. So now let's think about how to map a block to a set. Okay. So this will be achieved through some kind of a cache indexing function. So remember that each block in memory can map to only a single set. So therefore, our goal is to find the set index. The set index is calculated typically using the following function. So you take the block address, okay, and you do a modulo with the number of sets. Now notice that if the number of sets is power of 2, then the indexing function is very simple. It's essentially just selecting a few bits or a particular set of bits from the block address. Okay, so let's look at an example. So for example, we have, say we have 2 kilo sets or 48 sets and 64 byte blocks. The block offset, okay, so first of all, let's think about what is the block size. So the block size will be some number, let's say 64 bytes or 128 bytes. And you will use some of the bits to index a particular byte, okay, in the block. So therefore, you essentially have, you know, this portion right here for a block offset. And block offset is calculated by the log 2 of the block size. Okay, so for example, if you have 64 byte blocks, then you're going to use 7 bits of the address just to identify which particular byte you want to access in the block. Now, but you know, the rest of the address is essentially a block address. This is called a block address. So this is the one that is modulus with the number of sets. Okay. So if the number of how many bits are used for the index, for the set index, this will be the log 2 of number of sets. Okay, that's because the number of sets is power of 2. Now, all the remaining bits, these are unused. Essentially, this is unused for the purpose of indexing the set. So what is this used for? Then this will be used for to identify, you know, which block. So remember that there are many blocks that can map to the same set. Now you need to be able to distinguish them. So the tag essentially remember which block are are placed in a cache right now. All right. So these are an alternative view of cache indexing. Okay, so there are other cache mapping functions that is possible. So the one I showed earlier on the earlier slide is this one, traditional cache indexing, where you split the address into block offset, index, and tag. Okay? There are other ways to index a cache. So for example, you could use prime modulo indexing. So prime modulo indexing works this way. So you essentially, instead of power of 2 number of sets, you're going to have prime number of sets. Okay? So prime number of sets. What's the advantage of prime modulo indexing? Now, if you know, programmers sometimes allocate an array or matrices that are also power of 2, or maybe not, they are not power of 2, but they are not prime relative to the number of sets, meaning that if you have striding accesses, then it turns out you're going to be accessing certain sets but not others. So the cache are not fully utilized, or the sets don't receive the same number of accesses. Okay, so you overutilizing some sets and underutilizing others. With the prime modulo indexing, the idea is that a lot of the structures, array, matrices, and so on are very unlikely to have a prime, prime size. Okay, with the prime modulo indexing, if you have striding accesses, they will go to different sets. So then you have a much more uniform set utilization. So that's prime modulo indexing. But you can achieve similar thing by just randomizing how the set is selected from the address. So this is one example. So for example, you partition addresses into portions that you XOR them together to find the index. Okay, so this is another way of kind of randomizing or spreading around the accesses across sets. Okay, so research has shown prime modulo indexing performs the best in terms of spreading around the addresses mapping to the sets. However, the computation of prime, modulus with a prime, requires some overhead, extra hardware overhead. So XOR indexing kind of like gives something in the middle. So it's simpler to calculate, but it also has some feature that it spreads around accesses. Now, which one are used in the current processors? Well, usually what people assume is traditional cache indexing, but I know there are some processors that implement some kind of randomization. Okay, so perhaps not exactly the same function, but similar. Alright, now let's look at how cache works. Okay, so suppose in your program you have a load or store instruction to a certain address. So this is the requested address right here. And it's not that the address have different parts, but essentially we will use different parts of the address when we access the cache in different way. Okay? So this is the address given by the processor. Now because of this our number of sets and block size and so on, then we will split the address into different parts when we access the cache. Okay, so what are the steps? The first thing we need is actually the index. Okay, think about it. The block offset is not needed until we find the block. So the first thing we need to do is to use the index. So we take a few bits in the middle. Essentially, we go to the decoder to determine which set we want to access. Now, in this particular example, we have a two-way associative cache. Now, you will see that we have a data array that actually contains the data, but we also have a tag array. The tag array contains the tags or record the tags. So the purpose is to remember which blocks are currently cached in the data array. Okay? So first step, you take the index, you go to the decoder and find out, okay, so it turns out I want to access this. Okay? The next thing you do, okay, is to read out the tag from the tag array. Okay? So this will be read into the sense amplifier. Yeah? So once they are in the sense amplifier, okay, first of all, look at the fields that we have. First, we have the tag, we have the state, and we have the LRU bits. Alright, LRU bits I will explain later because they deal with replacement policy. And then the state, this deals with the coherent state that I will explain in the cache coherence module. So right now, just focus on the tag, okay, on this one right here. So you read out the tags. And then essentially the third step is to use the tag and then do a comparison with the tags that are pulled from the tag array. Now if they match, that means we have a cache hit, meaning that the block that we want is in a cache, either in the first way or the second way. Okay? If there is no match, then we have a hit. We have a miss, right? So suppose that we have a hit. Okay, so let's say this one match. If it matches, okay, then we have the data that we want. So we essentially go to the way that hits. In this case, the first way hits. So this is the data that we want. Okay. Not on way 1, but it's on way 0. We pull it down to the sense amplifier again, and here we will be selecting, which one of these we will take, right? So that happens when we return the byte to the processor. All right, now let's deal with replacement policy. So something to consider is the following. So suppose we miss in a cache, right? So now we need to bring a block from memory and we need to place it in the cache. Where should we place it? So that deals with the replacement policy. The replacement policy essentially selects the block to evict to make room for a new block. So the policy that is often used or that is often assumed is LRU, or least recently used. Okay? So essentially it's a heuristic. Okay? So this recently used works this way. So among the blocks in the set, okay, among the blocks in the set, we choose the one that was least recently used and evict that to make room for the new block. Now why does it make sense to use LRU? Well, typically it performs well. Okay? The reason is because the data that we need, we tend to access a lot again and again. Okay? So the data that we have not used for a long time, so this is the one that the program has forgotten. The program may not need it. Okay? So usually it performs well. There is a problem. Sometimes when you have a working set that is slightly larger than the cache, in this case sometimes it degrades badly. Okay? So for example, you may have let's say two-way cache associativity, and then your access pattern is A, B, C, A, B, C, and so on. So notice that we have 3 blocks we are accessing, but there are only 2 ways. If we use LRU, in this case A will be brought in here, B will be brought in here, and then when we brought in C, A has to be evicted because it's the least recently used. So now we have BC, and then we have access to A. That will miss because we just evicted it. So when we miss, we bring in and we evict B. That's because B is the least recently used compared to C. So when we access B, we miss again, and so on. So in this case, if you have something like this, the miss rate will become high. So that's LRU. There's also FIFO, first in, first out. Doesn't do as well as LRU in most cases. Most practical implementation of caches actually use something like a pseudo LRU. It's an approximation to LRU. So LRU is somewhat more expensive to implement. It's a cheaper way to implement than LRU. It behaves similar to LRU in terms of miss rates, but cheaper to implement. And then the idea here is to keep some tree of bits to record the most recent path to the block. Let's look at some example. Actually, before we go to the pseudo LRU, let's look at LRU. How can it be implemented in hardware? Alright, so the way it works is the following. Let's say we have a 4-way associative cache. So we're going to keep a 4 by 4 matrix, okay? Matrix of bits. So initialize it with 0 initially. Okay? Now, suppose that current cache content is block A, block B, block C, block D in way 0 all the way to way 3. But then we have an access stream BCAB. Okay? So initially our LRU matrix is all zeros. Okay? Let's say we have access to B. So what do we do to update the LRU? So when we access B, this is what we do. First, we find where B is. So B is currently in way 1. Okay? And then we do 2 steps. One is we find the row that corresponds to way 1, and then initialize this to 1. So this is all set to 1. And then we find the column where B is, which is way 1 right here. And then we zero out or reset the column corresponding to way 1. Okay? So that's how we maintain the metadata for LRU. Now, let's say the next access is access to C. So we do the same thing. So we find that, oh, C is in way 2. So we set the third row to 1, and then we reset the third column to 0. And the next access to A, we do the same thing. We find that A is in way 0, so we set the first row and then reset the first column. Okay? So that's how you maintain it. Now, suppose the next axis is D, and we find that D is in way 3. So we go to the 4th row, set it to 1, and then reset the 4th column to 0. Okay? Now, from here, now we already know which block is the LRU block. Okay, let me see if we have. Yeah. So let's say if we have access to E. Okay, E is not found anywhere here, so we have to essentially make room for E. So we have to evict one of the blocks. How do we do that? Well, this is how this information is useful to us, right? So what you do is essentially sum up the number of ones in each of the row. So number of ones. In way 0 we have 2 1, 0 1, 1 and 3. Okay, so this actually tells the order in which things were accessed. So if you see that the one with the fewest number of ones, that's essentially the LRU block, right? So B, okay, block B, which is residing in way 1, is the one that was least recently used. Okay, so then to make room for E, essentially we evict B from the cache. So that's how LRU is implemented. It's definitely not the only way to implement LRU. Okay, but one thing to look at is that, you know, if you have n-way associative, the complexity of keeping all this information is essentially the order of n squared. That's the size of the matrix. Okay? Right. So here is a cheaper way of you know, having a replacement policy similar to LRU but not LRU. So this is pseudo LRU implementation. So we approximate LRU using a tree. Okay? The pseudo LRU complexity is less. Okay, so in this case it's order of way. So how do we do that? Okay, suppose the cache content is 0, is like before, and then here essentially we construct a tree. The tree of bits, right? So the tree essentially indicates the path that it takes to access the block, right? So when we are accessing the cache, then we use the following meaning, right? So 0 means left and 1 means right. Okay? So that's how we encode the path to the most recently used block. But when we want to replace, we use the least, we want to select the least recently used block, and therefore we flip the meaning of the bits, right? So instead of going to the left on 0, we go into the right, okay? And for 1, we go to the left. That way we try to avoid evicting the MRU, the most recently used block. Here is an example. Suppose our initial case is cache has a content of A, B, C, D. Now we want to figure out, we want to update the bits essentially so that we know which one to evict. Okay, so when we access B, now B is located here. So traveling from the root to B, you have to turn left and then turn right. That means you have to put a 0 here and a 1 here. When you access C, you have to turn right and then turn left. So then you, along the path, you put a 1 and then 0. If you access A, next you access A, let's say you have to turn left and then turn left. That means you put a 0 and 0. Okay? When you access D, you have to turn right and turn right. So then you program the bits as 1, 1. When you access B, then the same, you have to turn left and then turn right. So 1, 0. Now, suppose that now we access E, which is not found in the cache. So then now we have to evict something. Now if we look at the access pattern, the least recently used block is which one? Okay? the least recently, oh, wait a minute, we were right here, okay? So we were actually right here. So the axis is B, C, A, D. So the least recently used block is B. So when we want to find a victim, then essentially we go to the root of the tree and then read the content right here. Okay? The content is 1. Usually that means when we go to the left, but when we want to evict, we go to the sorry. 1 means right. So now we go to the opposite. So we go to the left. We turn left, and then when we see 0, we turn right instead of left. So then we identify this is the block that we want to victimize to place E. Okay? So E will be placed here to replace B. Notice that this is the same outcome as if we use LRU, but not always. Okay? So in many cases they produce the same outcome, but not always. So E is placed where B was, and then as you traverse the bits from root to leaf, you flip them. Okay, so this used to be 1. We flip them to 0. This used to be 0. It flipped to 1. Okay, so essentially we refresh the pseudo LRU bits. All right. Next item I want to talk about is the write back, write policy. So here we have a write through versus write back. Write policy deals with the following question: when do we propagate value in a cache to the next level or to the memory, if the next level is memory? So should we do it immediately, right? So every time we write to the cache, we immediately propagate it to the next level, or should we wait until we have to evict the block? So in the first one, that will be a write-through policy, right? So we write it to the next level. The other one is we just wait until we really have to do it, until we evict the block from the cache. That's the latest possible time you can write to the next level. So we just wait until the block is evicted. So that's called the write back policy. What are the pros and the cons? Now the write back policy tends to save or to conserve bandwidth. The reason is that you typically have multiple writes to the same block. Okay? So imagine you may have a block that is 64 bytes. Okay? If you have an array, let's say a double precision floating point, you may have 8 bytes per element. Now you can actually put 8 of them. You can have 8 array elements in the same block. So if your algorithm is such that you write to each array element, you're going to have 8 writes to the same block, okay, before, essentially while it's in a cache. So if we use write through, every time I write, okay, let's say to one first element of the array here, I propagate it down. Okay, that's a write through. And then I write to the next one, and then I propagate it down, and so on. So then you're going to have 8 write-throughs for this case. Now if we have a write-back cache, this doesn't happen, right? So with the write-back cache, you write in the cache. You don't propagate it, and you keep writing. And then at some point, this block will be evicted from the cache. When that happens, essentially, you write the whole thing, the whole block, into the next level. Okay? So then we only incur 1 write instead of 8 writes. So it tends to conserve bandwidth. Now the typical organization of cache will be something like this. L1 cache typically uses a write-through. This is because the bandwidth between L1 cache and L2 cache is not typically a big constraint. So you can afford to have a lot of wires going out from the L1 cache to the L2 cache. But there's another good reason for it, which is for fault tolerance. Okay, so the L1 cache is typically protected by a parity bit, meaning that it can only detect an error. Okay. Now imagine if you have a block that is clean and have not been written. If you detect an error, okay, let's say some alpha particle from somewhere hit the bit and flip it 1 to 0, 0 to 1. Okay. When that happens and you detect it, that's okay. You just get rid of it and read it from the next level cache. However, if you have a dirty block, meaning that the block has been modified and has not been propagated to the next level, if you detect an error, then that's it, right? You cannot recover from it. Okay? So this is, of course, you can also use a different kind of error, resilience, so essentially error correction code instead of error detection code. You could do that, but that slows down the access. So L1 needs to be fast, it has to be small, it has to be fast. So people like to use error detection code such as parity in L1 cache. But that means you cannot correct errors. Because of that, then essentially we can just use write through. So anytime we detect error, we just retrieve the block from the L2 cache. Now anything beyond the L1 cache, this is not as, doesn't have to be as small or as fast. So then we can use write back cache. So we conserve the bandwidth. Also, sometimes after the L2 or after L3 cache is typically we go off chip. So the next question about write policy for cache is the following. Write allocate versus write no allocate. So the question deals with the following. So when you have a store, you want to write something in a cache, do we bring the block into the cache or not? Okay, so this assumes that the block is not already in the cache. So for example, suppose we have a processor in cache and we execute a store instruction to a memory address that is contained in block A. Okay, so this is write allocate cache and write no allocate cache. In a write allocate cache, this is what we do. So we go to the cache, we don't find it in a cache, so we go to the memory or to the next level, and then we bring the block and we allocate it in the cache. Okay, and then after that you perform a store, so you modify part of the block. In a write no allocate cache, we don't do that. So essentially, here is the store. If we don't find it in a cache, we just keep going and then overwrite A in the memory. Okay? So A will not be found in the cache after the store completes, whereas with write allocate we will find it. So what is the rationale, or why do we even care about this? Well, it turns out that there are a couple of things. The first is that, first question is, why do we even bring a block that we are going to overwrite anyway? Okay, so imagine if you have a small cache block and then you want to overwrite it completely. So there's no reason to bring it to the cache and then write it. Okay, so this was the rationale for write no allocate. Okay? However, things has changed since then. What has changed? Cache block size has got a lot bigger. Okay? So with cache block size that has become a lot bigger, when you write, you don't overwrite the entire data in the block. Instead, you write only small portion of that. Because of that, then write allocate has been considered and has been proposed. So you bring the block, so the rationale is you bring the block and then you write the small part of the block. Hopefully, in the near future, you may write to a different part of the block, or maybe the same part of the block. and you may read from the block. Okay, so you may as well bring it into the cache, so that if any of this happens in the near future, you already have the block in the cache. Okay, so that's the the rationale for write allocate. And these days, because the block has become quite large, okay, 64 bytes quite common these days. So a typical cache organization use write allocate. Alright, so this ends our coverage of the first module, chapter 6. So we talk about basic cache architecture, how to address it, how the cache works, how to index it, how to replace a block, and a write policy. In the next module, we will look at other cache design issues, including inclusion policy and so on. Okay, until next time.